Okay, the next section of chapter 3 is section 3.3, differentiating inverse trig functions. So there are three main results, which you need to be able to derive. We're going to have a go at the deriving arc sine in a minute. Just to remind you, the arc sine, what it looks like. So your arc sine is looks like that. This is sine, and arc sine is going to be reflected in the in y equals x. So effectively you're going to get a shape like this. Okay, and normally you've got 1 here and pi over 2 here, minus pi over 2 here, and minus 1 here. This time they swap positions, so it's minus 1, minus pi over 2, and then 1, and pi over 2. So you can see that the domain is x's belong to the interval between minus 1 and 1, and the range is all y's belonging to the interval between minus pi over 2 and pi over 2. Okay, then if you think about cos, okay, so if I sketch cos, you need to sketch the part that's 1 to 1, so you're not going to sketch from minus pi over 2 to pi over 2, so you're going to sketch from 0 to pi, minus 1, 1, that's pi over 2. So this is y equals cos x. So the cos inverse, or arc cos, is going to be the reflection of this graph in the y equal x line. So the pi over 2 and pi will go on the y-axis, and minus 1 and 1 will go on the x-axis. So it's going to be, so 1 used to be, the graph used to start at 1 on the y-axis, now it's going to start at 1 on the x-axis. It finishes at minus 1 and pi, so minus y on the y-axis. So it finished minus 1 on the x-axis and pi, so let's say pi is somewhere here, and you need to draw a graph. I used to cut the x-axis at pi over 2, now it's cutting the y-axis at pi over 2. There we go. And you could see the domain is all the x's between minus 1 and 1, and the range is all the y's between 0 and pi this time. Okay, and arctan, I'll just draw arctan for you without drawing tan. So the asymptotes used to be vertical, now they are horizontal, and they are at minus pi over 2 and pi over 2, and the graph looks like this. So the domain, you will have all the x's belonging to the real values, no restrictions. Range between x, sorry, y is between minus pi over 2 and pi over 2. You want to use set notation, interval notation, like you did over here, then you do curly brackets to show that it's you don't want the end points to belong to this interval. Okay, just a quick note here, the arc sine differentiates to 1 over square root of 1 minus x squared, and arc cos is just the opposite in value, but exactly the same. Very, very interesting. I think all three results are in the formula booklet, but obviously it might be useful to learn them. You definitely need to know how to derive these results. So here's the first one. We are going to show that arcsine differentiates to 1 over 1 minus x squared. So there's different ways of doing it. The one you can probably relate to, and I think in normal maths you also need to be able to do that. Let's just, so it is y equal to sine inverse of x. So before you got to that, you had sine y is equal to x. And now you've got two ways of doing it. You can either differentiate an x to get into, with respect to y, and you're going to get cos y, and then you need to, we want to find dy dx, so we're going to flip it. So it's going to be 1 over cos y, and we're going to eliminate y because it's in terms of y, we want it in terms of x. So if cos y is equal to 1 minus sine squared y square rooted, using our first identity we learned about wind trig, and then replace that with x, the sine with x. Okay, and then pop it over here. Alternatively, you could just use implicit differentiation. So you differentiate sine to get cos y dy dx, and that's equal to 1. So you get dy dx is equal to 1 over cos y, and then you proceed the same way as here. Okay, so let's have a look at example 7. This time we're going to differentiate arcsine of x squared. Note this is sine of x squared. So we're going to use, first of all, implicit differentiation. So we're going to again rewrite it by putting sine y is equal to x squared. So implicitly that will go to cos y dy dx, and then to x. Make dy dx the subject, and eliminate y. So 1 cos y is equal to 1 minus sine squared y. We've got sine y is equal to x squared, so you've got 1 minus x squared squared, so it's 1 minus x to the power of 4, which is 2x, 1 minus x to the power of 4. Okay, so this is actually part A. Part B, we're going to arrive at the same result by using chain rule plus the standard result, i.e. So always quote anything you're going to use, quote it in your workings out. So I'll do the chain rule. Not going to do it quickly, do it slowly. So I'm going to use u for my x squared, and du dx is going to be 2x, and then if I substitute it instead of u x squared, then I'm dealing with y equals to arc sine u. So we're going to find dy dx. Let's actually find dy du first. Arc sine is 1 over 1 minus u squared, square rooted. And now the chain rule states that dy dx can be obtained by multiplying dy du by du dx. So we've got to do dy du, which is 1 over 1 minus u squared square rooted, multiplied by du dx, so 2x. That gives me 2x in the numerator, and in the denominator I've got 1 minus u squared, but u squared is equal to x squared squared, so x to the power of 4. There you go. Proven. Both ways are perfectly good in solving those kind of questions. So let's move on to example 8. We've got to now find dy dx. I don't think we haven't been told which method to use, so we are going to use just one method, whichever one I pick, I guess. Okay, so you could use the formula. You could use rewriting tan y equals 1 minus x over 1 plus x. I'm going to use the formula. So if I put dx of arc tan x is equal to 1 over 1 plus x squared, because it's a nice and neat formula. So we're going to use chain rule. So let u be equal to 1 minus x over 1 plus x. And then your y is going to be arc tan u. Quotient rule, which, let's just quote it. Oh, I've used u. That's okay. I'm going to use capital U in the quotient rule, so no, it doesn't matter. We'll use u over v. vu dash minus uv dash over v squared. What we can use here is maybe do a u1, just so we make it different from this u. Okay, so our du dx will be, so v squared, this is going to be my v, and this is going to be my u. So v squared is 1 plus x squared, and then we're going to take v, which is 1 plus x, and multiply it by u differentiated, so minus 1, minus, then we're going to take u, which is 1 minus x, and multiply it by v differentiated, which is 1. Okay, so you're going to get minus 1 minus x, minus 1 plus x over 1 plus x squared. This gives me minus 2 over 1 plus x squared. Okay, dy du, that gives me 1 over 1 plus u squared, directly from our result over here. If u is equal to 1 minus x over 1 plus x, let's just rewrite it in terms of x. So let's get rid of that double-decker fraction by multiplying it by that denominator, by 1 plus x squared, 1 plus x squared. That will give me 1 plus x squared on the top, and then 1 plus x squared plus 1 minus x squared on the bottom. So this one here will go, I'm afraid we have to expand it, so you're going to have 1 plus 2x plus x squared plus 1 minus 2x plus x squared the middle terms cancel. You've got 1 plus x squared over 2x squared plus 1. Perfect. Okay, let's put the two together. So dy dx by the chain rule is the product of those two derivatives. So you get dy du multiplied by du dx. So dy du is this 1 plus x squared, so it's the second part, over 2 times x squared plus 1, multiplied by minus 2 over 1 plus x all squared. Cancel, cancel. You're left with minus 1 over x squared plus 1. And I think that's the last example, which will lead to exercise 3C. I'm going to actually show you the other way that I mentioned. If you move the tan on the other side, what you might find that this is going to be a little bit easier. So the alternative method, if you rewrite it as tan y is equal to 1 minus x over 1 plus x, and then you can use implicit differentiation. So you've got sec squared y, and over here we've already done that part, so I can just quickly, it's minus 2 over 1 plus x squared. Now we need to get rid of the forgot dy dx here. Get rid of sec squared. Let me just write it like this first of all. Okay, so sec and tan like each other. 1 plus tan squared is equal to sec squared. So we've got tan being 1 minus x over 1 plus x, so it's 1 minus x over 1 plus x squared. That's what sec squared can be replaced by. I can bring it to the common denominator, so I've got 1 plus x squared plus 1 minus x squared over 1 plus x squared. That's what our sec squared. And I've actually done that before. We've expanded it. The 2x from this expansion and minus 2x will cancel, and we're left with 2. And then you've got 1 plus x squared. So it's very similar to the one before, obviously. We can put it together, minus 2, 1 plus x squared times this expression, so 2 times 1 plus x squared over 1 plus x squared. So this is multiplication is within the denominator, so we're going to cancel that, and you're going to be left with minus 2 over 2 times 1 plus x squared, and that cancels again, and you've got minus 1 over 1 plus x squared. You don't need those brackets. Perfect. So now you can definitely move on to exercise 3C, and I will make another video going through some tricky parts, or at least give you hints as to how to approach them from that exercise. So have a look, have a go at the exercise first, and then if you get stuck in the video, and if you still can't get it or got stuck on other questions, let me know and I'll help you.